Welcome everyone to GIA Knowledge Sessions, a series of talks and seminars about gemology fueled by our decades of research. At GIA, we consider ourselves so fortunate to study and learn from gems, and it's our mission to share our discoveries and learnings. I'm excited to kick things off today. I'm Dr. Sally Magana, Senior Manager of Diamond Identification, and I'm joined by Dr. Mike Breeding, Senior Research Scientist, and he's going to tell us all about the challenges of melee-sized diamonds. Now, before we get started, just a bit of housekeeping. Everyone attending this is automatically muted. If you have a question, please submit it using the question and answer feature you'll see at the bottom of your screen. Feel free to ask questions as we go. There will be a Q&A session at the end where Dr. Breeding will have the opportunity to answer some of your questions. We will also send a recording of the session to you later today, and that message will also have a survey, so we'll love to hear your feedback. And with that, I'm going to pass you over to Mike.
Hi, everyone. Thank you for attending GIA Knowledge Session. It's always fun to have the opportunity to share knowledge and information with you guys out there who on a daily basis are looking at diamonds and trading diamonds, and hopefully this information is really useful to you. So normally we like to talk about the biggest, brightest colored diamond we can find, but today I'm going to do the exact opposite of that. I'm going to talk about perhaps the smallest diamonds that I can find. Those are melee diamonds. And they may seem somewhat insignificant, but particularly in the last few years, being able to understand and identify melee is really important because of the introduction of much higher numbers of lab-grown diamond into the market. And particularly in these very small sizes that are difficult to identify and separate, that can be quite a challenge. So with that, I wanted to show you this beautiful picture of all these large gemstones. So just the opposite of what I said, right? But when you look at all this jewelry, the first thing that comes to mind is you notice the vibrant blues, the large pearls, emeralds. You notice the center stones, the really focal points of the jewelry. But if you take away all of these small diamonds, all of these melee stones that are accenting this jewelry, most of the sparkle is gone. These sort of supporting cast, behind the scenes players, the melee in the jewelry, are what give it a lot of its pizzazz. And just as it's important for the center stones to be very well understood and properly identified, it's become more and more important that we know exactly what these melee are, whether they're natural or whether they're grown in a laboratory. So what are melee diamonds? Well, it's not a really well-defined term. Simply put, melee are very small diamonds. And I guess very small could sort of be in the eye of the beholder, or perhaps in the eye of George Washington here, as you see this very tiny melee diamond on this quarter. Just kind of really goes to show how small these stones are. This one's actually half of a point in size. GIA defines melee diamonds as faceted stones that are less than about 1/5 of a carat, so 0.2 carats. So everything below that. And diamonds, we've seen diamonds faceted as small as 1/10 of a point, or 0.001 carat. Some really, really tiny diamonds when you think about it. But just like the larger stones, it's important that we know whether those are natural or grown in a laboratory. Melee diamonds tend to primarily be round, though not always. In days gone by, they were often cut with 17 or 18 facets in a single cut form. This is largely when a lot of cutting and polishing was done by hand, and it was not so easy to work with these very tiny stones. Now, with a lot more machine cutting involved, most melee is cut into a modern brilliant cut with 57 to 58 facets, depending on the presence or absence of a culip. So much more typical, even in these very tiny sizes, the stones, the round brilliants still look very similar in cutting style to the larger stones. So several years ago, if you were to obtain a pile of melee like this, you'd have really little concern with this. Just assume that they're all natural because there's so many of these small natural stones available. But like I said, now it's very possible that small bits of these stones, or even in some cases, hopefully properly disclosed, large quantities of melee like this can actually be laboratory grown. As far as natural stones go, I like this image because it kind of shows you a nice size distribution range. You see a few large stones. Everything here is mostly brown, yellow, or colorless, which are the most common colors of natural diamond. But you see there's all kinds of these small little octahedron here. And you can't cut a big stone out of these. You can only cut a very small stone or a couple of small stones. And that's where all this natural melee comes from. Either that or from off of the larger stones when they're faceting bigger gems. And to give you an idea of just how much of this there is, this is an image from the sorting house near the Lomonosov mine in Russia. And you see that all the larger stones are all separated out by size and by color and by quality here in the bottom. And you notice there's a loop for scale. Notice these two bins that don't really catch your eye initially at the top. Those are all melee diamonds, just massive, massive quantities. I mean, look at the amount of melee here relative to the amount of larger stones that's produced. So the majority of diamonds that are coming out of diamond mines are actually melee diamonds. It's pretty amazing when you think about it. So that being said, and I've mentioned a couple of times already that you can have natural melee, you can also grow melee in a laboratory. And if you've seen some of my previous talks, lab grown diamonds, you've seen this diagram before. This is a phase diagram for carbon. And remember, diamond is made out of pretty much completely carbon. So pressure increases upward, temperature increases to the right. The area in the red is where graphite would form if you have carbon. And the white region is where diamond is stable. These are pressures and temperatures. Natural diamond grows at about 5 to 6 gigapascals, or about 150 to 200 kilometers in the earth, and about 1,000 degrees C. We can grow diamond in a couple of different places. Practically, we either grow in this teal colored field or in the yellow colored field. The teal field is where high pressure, high temperature lab grown diamond is created. So similar pressures and temperatures to natural diamond, though slightly higher in temperature range, because we don't want to wait millions of years for those diamonds to grow in the lab. And then a little more on the crazy side is way down here in the graphite stability field. Through some carefully controlled methodology, you can actually grow diamond at below atmospheric pressure in the graphite stability field. So we'll talk a little bit about both those as a slight review as we go forward here. A little bit of a history lesson. Way back in 1952 is the first known growth of a laboratory grown diamond. It was a tiny, tiny CVD diamond grown by William Eversole at Union Carbide. Shortly thereafter, in 1953, 1954, a Swedish company and then GE produced very tiny, high pressure, high temperature lab grown diamonds for industrial use. And then it was another 16 years or so before 1970 when General Electric introduced its first gem quality, high pressure, high temperature lab grown diamond. So a lot went on in between then and 2015, but if we kind of cut to the chase, in 2015 and 2016, we started to see really large lab grown diamonds. So up to over 10 carats grown by high pressure, high temperature, and over 5 carats faceted grown by CVD or chemical vapor deposition. So we've talked about these in the past, but what's really remarkable is in 2017, so just 3 years or so ago, we started seeing massive quantities of very, very tiny melee diamonds coming out of largely from China. And we're talking on the order of 200,000 carats per month. And the production now is even larger than that. But in the past, it had been possible to grow tiny diamonds, but it was very difficult to grow colorless or near colorless tiny diamonds. And that's what this advance really was about. So let's talk a little bit about the growth techniques. And this will just kind of be a quick overview. High pressure, high temperature growth basically is trying to mimic the conditions within the earth. So we have pressures of 5 to 6 GPa, which is very similar to what happens in natural diamond growth. So about 150 to 200 kilometer equivalent in the earth. and the temperatures of about 1300 to 1600 degrees C. So a few hundred degrees hotter than the Earth facilitates faster diamond growth so that you can actually do it in a laboratory. To get these high pressures, you have to put the diamond materials into a very advanced press so that you can obtain the pressure. And at the same time, you have to control the temperature. On the left here, you can see this is how they would grow a single larger lab-grown diamond. You have a seed crystal, which is diamond. To grow diamond, you need diamond. A flux material to facilitate the transport of the carbon from the carbon source down to the seed for growth. The whole thing typically is under a temperature gradient where the top is hotter than the bottom. And this causes the carbon to migrate and to crystallize. So in a nutshell, you can grow a diamond in days to weeks, a decent sized diamond on the order of a carat or more. Well, with melee diamond, it's a bit different. And they first started growing melee diamond as industrial melee. So what exactly is different about that? Well, for one, they don't use a seed crystal. So they don't have to have that diamond seed at the bottom. They just get the carbon to spontaneously crystallize as diamond all through the chamber, and it makes lots and lots of diamond. As a result, they also don't have to control the temperature gradient very carefully. Since we're not having to maintain growth over a long period of time, we just want tiny little crystals, they can just nucleate and grow. They do use the catalyst, the same as larger nickel, iron, cobalt metals. It causes this process to be possible at much lower pressures and temperatures. And then just to give you an idea, it takes about an hour to finish one run of industrial diamond growth. Many, many tons of this material is produced annually, and most of it, probably 99%, is produced in China. This type of diamond is very inexpensive. It can cost as low as 12 cents per carat. And if you think about a carat of diamond this size, it's quite a lot. Well, what do they use industrial grade diamond for? Quite a lot of things, and interestingly. They use it to coat wire saws, to coat saw blades, grinding wheels. As micro bits, it can be added to diamond drill bits. Each one of these black discs in this drill that they would use to drill down in the earth. All of those are made of multiple diamond crystals, all centered together. So it can be used in scalpels for medicine. The applications are just endless, really. Here's an idea of what some of that more industrial quality stuff looks like. It can be gem quality when it's grown a little larger, these yellow stones here on the lower left. But you see they're still very, very tiny. They're yellow because they incorporate nitrogen during growth. When you grow in these presses, as you see on the right, these are green, large metal devices. This is from a factory in China. When you grow this material, there's nitrogen in the atmosphere. It gets incorporated very readily into diamond unless you take a great deal of effort to prevent that from happening. So for this very small industrial stuff, they don't really do that. If you go and you look in a very high magnification scientific microscope, you can see the tiny little crystals, and they have very distinctive cube octahedral shapes, meaning the mixture of a cube and an octahedron, which if you've tuned into previous talks, you know that's a very classic growth shape for high pressure, high temperature lab grown diamonds. It's very characteristic. Well, after growing enough of these, 2017, someone developed a technique whereby they could actually grow colorless versions of this relatively easy. And what's really funny is they used these little tiny yellow, more industrial diamonds as their seed crystals for these. And you can see them when they come quite often, these larger crystals of near colorless material have the seed still attached. And so it's really cool. You get to see the initial thing that they were able to grow, and then what they used that to grow the larger stone that they would cut faceted melee stone from. More than that, typically larger lab-grown, HPHT lab-grown diamonds have to be grown on the cube face. They need to start on the cube face, like this is oriented. That's a cube face. But with these small stones, they developed the technology to be able to grow on any face pretty much, either the cube or the octahedral face, as you can see in this. The crystal shape is slightly different, but it's still facetable into a very nice near colorless melee stone. So it's really quite an advance that was made 3 years or so ago to really facilitate the production of large amounts of this colorless melee. So here's to give you an idea of what's produced. On the left, you see this is an entire bag of crystals. These are lab grown near colorless diamond crystals. All are 2 to 3 millimeters or so in size. In the image on the right, you can still see that many of them have their seed crystal still attached, the little tiny yellow flecks. This is just getting produced in large quantities by many companies in China. Here's another image to just kind of give you an indication. On the left, you now have the same thing with most of the seeds removed. They take those stones and they facet them into the melee that you're used to seeing in jewelry. The faceted melee end up being about 1.5 millimeters in diameter. So they range from about half of a point up to 1.5 to 2 points in size. So very typical melee size. But just from the quantities I'm showing you and the 200,000 carats per month, you get an idea that there is a lot of this HPHT lab-grown melee floating around and available. The other major growth technique is chemical vapor deposition, or CVD. It's a little more complicated in that it involves a reaction chamber with a plasma in it. It's a gas phase chemical reaction where you have to use hydrocarbon gases like methane to introduce the carbon. And you have to have a hydrogen gas also, which is kind of like a broom. It kind of cleans off the surface of the diamond seed crystals that are in the bottom of the chamber, allowing new carbon to attach to it in a structure and thus grow the chemical vapor deposition diamond. This entire chamber is kept under vacuum, so it's below atmospheric pressure, as much as a 20th to a 4th of atmospheric pressure. Temperatures are a little lower than natural diamonds at around 700 to 1,000 degrees C. But you can grow diamond here in days to weeks as well. The plasma is generated typically by a microwave source. And this plasma is where all of those gases are dissociated, meaning that the elements are broken up. So you free the carbon, you free the hydrogen to work on the diamond seed at the bottom and grow diamond. So here are a couple of examples of what CVD diamond looks like. On the left, the whole thing is a CVD diamond. The brown bit at the bottom with slightly different growth conditions than the near colorless bit at the top. Over on the right, the yellow on the bottom is the seed crystal. This was an HPHT synthetic seed onto which they grew colorless CVD. But the reason I show you these is not so much for that, but to give you an idea of how you may come about melee from this sort of growth. So you might envision that on the left, they may cut a fairly large stone out of the CVD, but then they've got all the side material from which they can facet melee-sized stones. On the top, the layer is so thin that it won't accommodate a larger stone like this, but you could cut several melee stones from it. Also, we're aware that certain growers are actually creating sample plates like this. This is that substrate plate in the bottom of the CVD reactor. Each of these little holes, they put an individual seed crystal to grow an individual CVD diamond. And each one of those is then faceted into melee. So it's both a byproduct of larger pieces as well as grown intentionally. With that being said, there is significantly less CVD, lab-grown melee, in the marketplace than there is HPHT-GROWN. It's just not as cost-effective to grow melee by CVD. And with techniques that have been advanced in China, it's fairly easy to do it by the high-pressure, high-temperature method. So either as byproducts or produced intentionally. Here on the right, you see 30 carats of CVD melee, so it obviously exists, but it is significantly less abundant. So with all that being said, kind of the point of this talk was to discuss some of the issues that come along with trying to identify and screen melee. And you can imagine when you're dealing with stones this small, this is a US dime, a 10-cent piece for comparison, and these stones are not much larger than the thickness of that dime, if that. Or these stones that are mounted in the side of this ring shank. It's very, very hard to access these types of materials. So some of the challenges, I mean, these may seem obvious, but the small size makes it very difficult to see inside these stones. So if they're loose, even when they're loose, they're hard to see inside, to see inclusions and things like that. The small size doesn't really provide enough material for many analytical instruments. So if you take these diamonds and you put them in a typical FTIR instrument, quite often you don't sample enough material to get a good signal to see what you need to see. The small size makes it difficult to handle and to analyze these stones individually. So it's kind of a joke where I say these tiny things are easy to lose, but it's the truth. I mean, if you've ever dealt with melee, it's very, very easy to completely misplace one just in a split second. And finally, the amount of time that it takes to analyze a single stone that's about 1 point in size is at least 2 to 3 times longer than it would take to analyze a half-carat diamond. So these tiny, tiny stones, which are worth significantly less than larger diamonds, take 2 to 3 times longer to actually identify using the normal techniques. So these are some of the major challenges. And so now I'm going to go through a few of the ways that we typically identify lab-grown diamonds and show you how that's problematic with melee. And I'll point out that I'm not really going to talk much about CVD melee because for a couple of reasons. One, CVDs in general don't have a whole lot going on in them for identification, making it a challenge unto itself. But the vast majority, I mean, 90+% most likely of the melee that's in the market in the near colorless melee is HPHT lab grown. So we're going to focus on that. So if you're familiar with lab grown HPHT growth at all, you know that we get a cube octahedral shape, as I showed you earlier. It's a byproduct of the way the stones grow from the seed crystal with cube faces and octahedral faces. Well, when you cross section that, you cut it to facet it, you end up with very distinct patterns where you have squares and sort of arms coming off the corners of the squares. And so these different regions will take up impurities like nitrogen and boron differently, and thus they tend to fluoresce differently. So you can see this pattern in a fluorescence of a lab-grown diamond. And here are some examples along the top. You see the nice cube sectors and then the large octahedral sectors fluorescing different colors. And this lends to showing you a very nice square with arms or a cube octahedral growth pattern. They also quite commonly phosphoresce, and this is due to the uptake of some boron during the growth process. Small amounts of boron can create large amounts of phosphorescence. You can contrast this with natural diamonds on the bottom. They tend to have purely octahedral growth, where we have a nice sets of interconnected squares where you cut across the octahedral growth. Natural growth zones do not resemble these in HPHT lab-grown diamonds really at all. So, but these are larger diamonds where you can very clearly see these growth sectors. What happens in melee stones? Well, here are some examples of melee. These stones are about 2 points each, so they're even fairly large for some of the melee that we see. And I think if you look across through here, you see there's some patterns in some of them, perhaps like this one. You can see a nice cube sector, maybe some octahedral sectors, not clear. But other stones like this one down here, if you looked at that fluorescence image and you tried to pick out a pattern, you'd be hard pressed to find anything. And so the point is these stones are so small that even the characteristic cube octahedral fluorescence patterns are not particularly useful in most cases for identification. The color of the fluorescence, mind you, is very useful, but not so much looking for the pattern. And speaking of color and fluorescence, that leads me to a discussion of one of the other major ways in which you can try and identify HPHT lab-grown diamonds, and that's by that phosphorescence. These previous images, these are diamond view images, meaning they're deep UV or very high energy UV. This pile of melee was actually done with a handheld shortwave UV lamp. And phosphorescence occurs not while the lamp's on, but after you turn the lamp off, if the diamonds continue to glow afterwards. That's called phosphorescence. So the shortwave UV lamp was turned on this pile, then it was turned off, and this is what you see after the light's turned off. So this phosphorescence is a very distinctive property. It's not unique to HPHT lab-grown diamond, but it's very common, and it's due to trace amounts of boron. But you notice most of this is blue phosphorescence, but a few of these are phosphorescing blue or orange, right? So what's the difference, and how do we know? Well, as scientists, of course, we can't be happy just to say, oh, well, some of them are different. We go and we look. And so these are some fancy plots, but basically color is from 400 to 700 along the bottom. So 400 being blue, 700 being red. So you see we're over here on the blue side with these peaks rising up, and going up the side is the delay time in the phosphorescence, meaning at 0, when the phosphorescence is strongest, it decays. So the phosphorescence slowly goes away. But you see a very distinct hump in all of these blue phosphorescing diamonds, right? And what's cool is if you look at the time, it goes, in most natural diamonds, the phosphorescence, if it's present at all, decays within a second or two. These are going strong at down at 20 seconds. And then if we look at the same plot for those stones that are fluorescing yellow-orange, you see it looks very similar, right? It has this 500 nanometer band in the blue, but it has this little shoulder that's extending off at 570 nanometers, and it causes the whole emission to extend out so that you have more red or orange added to the blue, and thus you get a yellow or an orange color. So just this subtle little combination causes the phosphorescence to be yellow-orange instead of blue. But this plot really gives you an idea of how long-lived the phosphorescence can be from HPHT lab-grown diamonds. Notice the scale now is extended all the way out to 50 seconds. So even at 50 seconds, there's still some phosphorescence being emitted. That's a long time. That's almost a minute after you turn the UV lamp off. So phosphorescence is a very useful tool for looking at lab-grown diamonds. That being said, it differs by manufacturer. And here are a couple of examples. These are a couple of companies in China that produce these HPHT near colorless stones. And you have phosphorescence in some cases to long wave UV, this sort of orange yellow here from this company. But notice this company shows none. However, the phosphorescence to the shortwave UV is a fairly similar greenish blue, bluish green color, and with a few oranges interspersed. But my point is, phosphorescence is persistent to shortwave UV, but it does vary from company to company. Not only that, a couple of years ago, this Diamond Services Organization issued a lab alert where they said that if you expose some of these HPHT lab-grown diamonds to irradiation, they will no longer phosphoresce at room temperatures. So basically, you can use irradiation to quench the phosphorescence. And if you're using this phosphorescence as your identification tool, that's pretty much a big problem. So not to take somebody's word for anything, we've done our own experiments, and indeed, we did see something to that effect. Maybe not to the extent that they're alerting, but here's the blue phosphorescence in these 3 stones before irradiation, and after irradiation, you notice it's much lower and almost completely gone in the stone on the right. So it's certainly something to keep in mind, is that while phosphorescence is a valuable tool, it's not a tell-all. It's really not a tell-all when you consider that there are some natural diamonds that also phosphoresce blue, particularly rare type 2B diamonds that naturally have boron in them. So it's always good when you're talking about these things to keep everything in mind. Another major identification tool for HPHT lab-grown diamonds is looking at inclusions. Little bits of the metallic flux, that iron, cobalt, nickel catalyst that they use to be able to grow these at decent temperatures and pressures, it gets trapped like inclusions. Just like natural inclusions, these are lab-grown inclusions. Bits of metal, all irregular, strung out, reflective. It's very distinctive when you see it in a lab-grown diamond. Well, it's there in melee-sized diamonds. Here's a 2-point melee stone. And you see there's all sorts of little tiny bits of black material in here. And this incidentally is a lab-grown melee stone. But I don't know about you, but I wouldn't want to stake my reputation on being able to say that these little black blebs are laboratory-grown remnants as opposed to some sort of natural graphitized crystals or something. So the point is these stones are so small that even though the inclusions are there, you can't always tell, even in the microscope, if they're laboratory grown flux inclusions or not. Well, as scientists, once again, we have to geek out a little bit and go high tech. And so this is a scanning electron microscope image where we can look at very closely at the surface of one of these lab-grown melee and go in and measure the chemistry, the actual elements that are present in these little boxes. And when we do, we measure things like iron, nickel, cobalt, things that don't occur commonly in natural diamonds, certainly not in these combinations. And so we know that, yep, this is metallic flux that was trapped in that diamond. But most people certainly don't have the access to this type of instrumentation, and they certainly can't afford to do it on these tiny little 1-point melee diamonds. What's interesting is if you look at one of the highest concentrations, though, is iron in the flux. And we always talk about using a magnet sometimes to separate lab-grown diamonds. It usually doesn't work because there's usually not enough iron inclusions in there to attract the magnet. But in the case of these melee, it actually does work sometimes. And you can attract these things, and because they're so small, there's enough metal to pull them to a strong magnet. And so I had to put this in for fun. If you remember the magnet doodles or the iron firelings toys that a lot of us played with when we were younger, kind of get this idea of use a magnet, you move around the iron, right? Well, if you get a bag of HPHT-GROWN melee, sometimes you can do the same thing. There's enough iron metallic flux inclusions in these things to make them stick to this magnet and start to get dragged around like one of these toys. So it's kind of a fun little video that our moderator, Sally, put together, just illustrating this point. So I thought you might like that. But it can be a useful tool because it's almost certain that if you attract a melee diamond to a magnet, it's almost certain that it's not a natural diamond. So it's a good thing to keep in mind. So finally, one of the other things that we use and we try and teach people to identify HPHT lab-grown diamonds is by looking at strain. That is putting the diamond between two cross-polarized sheets and seeing how the deformation in the diamond structure affects the light going through. If the diamond is perfect, you will not get a pattern or colors. If the diamond has been deformed, you will get all these patterns and colors. So natural diamonds, and unfortunately CVD, lab-grown diamonds, will show these patterns just because of how difficult the growth is in those conditions. But HPHT lab-grown diamonds show no patterns or colors. And this is a very diagnostic way to identify HPHT lab-grown diamond. Unfortunately, once again, the size of the melee just kill us. Most melee diamonds are just too small to see these patterns even when they're present. It's hard enough to hold the melee diamond in the microscope between the polarizers, let alone try and see anything in it. So I think from those, you've seen that most of the things we do to identify lab-grown diamonds, particularly HPHT diamonds, don't always apply to melee, making it quite an identification challenge. That's not even to say anything about when you have a piece of jewelry like this, where all these melee are mounted and you can't take them out. How are you going to know that this one stone here is an HPHT lab-grown diamond? You're probably not. And even the people who identify them have a hard time. In this case, we can use fluorescence and phosphorescence in the diamond view instrument, and it singles out this diamond. But once again, we have to be careful to make sure that we're not dealing with potentially a natural type 2B diamond that may have phosphorescence as well. So that brings us to screening instruments. And there's a lot of screening instruments available right now, and they're designed mainly for this purpose, is to try and separate these tiny little lab-grown melee, natural melee. You can imagine if you're working with a watch like this that has all these tiny little diamonds in it. Beautiful, beautiful watch, but the challenges of identifying these tiny stones, and then under the glass even, these tiny stones. So to get a good screening technology, you have to meet a few requirements. First, it has to be accurate, obviously. It has to be efficient. I mean, if you can't do this reasonably quickly, then you're going to be doing it all day, especially most people aren't just selling one watch or one ring. They're doing a lot. It has to be reasonably priced, affordable. It has to work with loose stones or mounted stones, because melee quite often come mounted. And it has to fit a variety of users. For instance, this watch analysis would be very, very different than someone with a ring or someone with loose melee. The premise behind a lot of screening comes back to the chemistry of the diamond or the impurities present or the diamond type. And this is a very useful thing to know in general. I'm not going to go into much detail, but diamonds that have nitrogen impurities in them are type 1A, which is shown in gray in these pie diagrams. And diamonds that do not have nitrogen impurities are type 2. They can be type 2A or 2B, depending on the presence of boron or not. But the gist of it is, we're just talking about colorless and near colorless meli here, but all HPHT lab grown and pretty much all CVD lab grown colorless meli are type 2, either type 2A or 2B, while almost all natural meli are type 1A, with only about 2% being type 2. So this into itself is useful. If you can have some notion of the type, you can immediately screen your diamonds. This is a very important thing. So there are a few types of screening technologies available in the instruments that are being marketed around right now. I'm not going to go into detail about these, but you can do UV transparency where you pass UV light through. Type 2A diamond is transparent to UV, type 1 is not. So if you can measure the transparency, you can immediately have an idea of what type you have. Same thing with UV visible absorption spectroscopy. Type 1A absorbs more in UV than 2A, and if you can quantify that, then you can separate the two. FTIR, or infrared absorption spectroscopy, that's the way that diamond type was defined. It's actually measuring the nitrogen impurities, absorptions due to the nitrogen impurities. So that's the fundamental way to separate the diamond types. These other two are kind of marginally related to diamond type. Phosphorescence, which is what I talked about a lot earlier, is a pretty common property, right? You can image that phosphorescence, so you can see that blue phosphorescence in imaging, or you can actually measure the peaks, and I showed you some spectra doing that, and how fast they decay, because natural diamonds, the phosphorescence goes away much faster than a lab grown. So those are techniques of phosphorescence, and the phosphorescence is related to some of the boron impurities in most HPHT synthetics, which goes back to type 2B, type 2. So it's linked to type marginally. And finally, fluorescence spectroscopy, which is what we've used in our ID100 instrument in GIA. This actually looks at the lattice defects that occur in natural diamonds, but not in laboratory grown stones. So detecting natural features rather than lab grown features. And this is tied to the type in that most of these lattice defects are a product of nitrogen, and nearly all natural diamonds, including type 2 natural diamonds, most of them have traces of nitrogen and traces of these nitrogen-related defects that cause fluorescence. So that's just kind of an overview for you of some of the technologies. This is a slide that I just threw together with a few different types of instruments. I'm not going to go into detail about these or talk about which one's better than others, other than to maybe point out the 2 GIA instruments in there, because those are the ones that I have familiarity with as I help develop those instruments. But you see there's a wide ranges of instruments and the size. I mean, this one's very small. Some of these are very large. Some of these give you different functions. But the gist of it is there's a lot of diamond screening instruments out there that are designed to make your life easier. But the question that immediately comes from that is, well, I don't know anything about these. How do I know what works and what doesn't? And you may ask me what's the best, and I can tell you about GIA's instruments, but I can't tell you about other companies' instruments. But fortunately, there is a resource available to you. The Diamond Producers Association, along with a whole bunch of other sponsors, including GIA, work together on something that's called Project Assure. And this is a testing and analysis of these screening instruments that are designed largely for meli. And if you simply Google Project Assure Diamond, you'll come up with this web address, and you can go there, and if you will see a list of all the instruments, and there's more than this. This is just all I could fit on the slide. Each instrument you can click on, and here's the example for the GIA ID100. When you go, it tells you a little about the instrument. It tells you what it can do, its capability, and then it tells you about its instrument performance, and particularly things like diamond false positive rate, meaning how many diamonds lab-grown diamonds did it call natural, and natural diamonds did it call lab-grown. So you want to see things like 0% there. And of course, it also talks about how many diamonds it will refer when it can't tell the difference and that sort of thing. But I wanted to make everyone aware that this resource existed so that they could really go out there and check for themselves. So that being said, the only instrument I can really show you much about would be the GIA instruments. And this is our ID100. It's based on fluorescence spectroscopy, and it's looking for natural features in a diamond. And in this little video, which was shot by our moderator, Sally, actually, she's analyzing a ring here and the Melee diamonds in it. And this gives you an idea. There's no sound, but you can see the visible response on the instrument that says pass, which means natural diamond, or refer, that means you need to refer for further testing. So it's a little bit of a slow video, but you see the diamonds are fluorescing to the UV light coming out of the instrument, and you're getting a pass result. Now she'll switch, in this stone she gets a refer result, so it would need more testing. As you switch from stone to stone, you can put the probe exactly where you want it and make sure that you're testing what you think you're testing. So it just gives you an idea of how these instruments work and why they're useful for Melee. It can be done with loose Melee just as well as mounted, but it's more impressive demonstration with mounted because that's really where one of the big challenges come. GIA also offers an automated Melee sorting service where we can sort lab grown from natural. In some cases, we can do color, we can do size, that sort of thing. And then you get your Melee stones back. You can send in large parcels and you get them back separated according to what the analysis reveals. And so here's another short little video just kind of showing you a tiny little piece of that automated technology. So it works from half point stones up to a fifth of a carat. And the stones just get automatically processed by a mechanized system that goes through and analyzes the stones and works to, the most important bit is separating natural versus lab grown or treated. So this sort of technology and service is available. So I just wanted to make that known to you. Obviously, you can't do that with mounted stones. So GIA also offers a service called their Quality Assurance Diamond Service. So if you had something like this pendant on the right that has a whole bunch of Melee set in it, you may use an ID100 and test a bunch of these stones and find that a couple of them refer and you don't know if they're natural or not. So then you mark those stones and you send them to GIA and you say, I want a quality assurance report. And then someone like me goes in and we use high-tech FTIR microscopes and photoluminescence and other devices where we can pinpoint each diamond separately and collect data and analyze them. And we determine whether they're lab grown or natural. And then you get it sort of in a table format. It's a fairly inexpensive service, especially for very small Melee stones, less than 6 points. So we're talking on the order of just a few dollars per stone kind of thing. So it's a very effective way to check some of these small stones. And I mean, I didn't talk about it a lot, but I mean, why would anyone care about 1 or 2 stones in here? I mean, if most of them are natural, it should be fine, right? Well, that's not the way the jewelry industry works. It's all about disclosure and reputation, and people should know what they're buying. And if you say natural, every one of the diamonds need to be natural. If they're not, you need to disclose otherwise. And that's where services like these are really important. And since these sorts of things aren't always available to the public in terms of screening instruments, then we offer this service to make that an affordable option. So for the last couple of slides here, I just wanted to show you a couple of different things just so I don't confuse you. See this is an entire parcel. These are all lab grown colorless diamonds, and they're not round, they're not single cuts, they're not round brilliants. These are fancy cuts, and Melee are cut as fancy stones as well. Don't assume that if you get your Melee as a tapered baguette or baguette that it's going to be natural, because they certainly cut plenty of lab grown stones in other shapes. Most of them are round, but not all, as you can see here. And they're not all colorless. I showed you yellow ones and colorless ones, but they can also come in a variety of colors. On the left, here's some of the faceted production from that Lomonosov mine in Russia that's famous for its pink diamonds, along with the Oriole mine in Australia. But you see, all these are natural pink Melee. Well, on the right, these are pink Melee as well, but these are laboratory, HPHT laboratory grown Melee that have then been subjected to irradiation and annealing treatment after their growth to turn them pink, and the colors can be quite comparable. So just because your diamonds are pink doesn't mean they're natural. So keep that in mind, even in melee sizes. So with that, that's about all I have for today. We will go back to Dr. Magana and hopefully field some questions.
Thank you very much, Mike. That was a lot of great information. We do have several questions from the audience. First one I'd like to mention is that one person asked that she's seen some diamonds that are observed to fluoresce dark blue under shortwave UV. Can anything be concluded regarding origin, such as natural or lab grown, based on that dark blue fluorescence under shortwave?
Well, no, it's kind of hard to say a whole lot just based on that. If you've heard some of our other talks, we talk about comparing the long wave UV reaction to the short wave UV reaction. Did you say fluorescence or phosphorescence, Sally?
Fluorescence.
Fluorescence. So typically with lab grown diamonds, they tend to fluoresce more strongly to long wave UV than short wave if they're natural. If you see it the other way around, where the short wave stronger, you should be concerned. Since there was no mention of long wave UV here, I will assume that you should be concerned, though it is not super common to see blue fluorescence under shortwave UV. But I'd advise this person to certainly have them checked out at a laboratory or someone with some analytical equipment that can do more advanced testing.
Thank you. Also, can you confirm that natural diamonds can be type 2A? And since diamond type is so important to screening, what should a person conclude from a refer result?
All right, so the first part of that question, absolutely natural diamonds can be type 2A. In fact, some of the most valuable and sought after natural diamonds are type 2A. Some of the largest natural diamonds are type 2A. Generally, they only comprise about 2% or so of the total number of diamonds, so it's pretty rare, but it certainly does happen. And as for a refer result, I'm assuming they're referring to from the ID 100 instrument. A pass result means it's a natural diamond. A refer result can mean a couple of different things. Since we're looking for natural features, a refer result simply means it doesn't have those natural features. So you could get one of three major conclusions. One, you could have a lab-grown diamond. Two, you could have a simulant, which is not a diamond at all. Or three, there's a very tiny percentage of natural diamonds that have other fluorescence features that are so strong that you can't see some of the natural ones we look for. And so occasionally you'll get a false refer from a natural diamond. But if you get a refer result from the ID 100, you should have it checked out in a lot more detail.
Okay. Thank you. You mentioned earlier some of the other instruments that are available for screening. Can most of these be used for mounted stones?
It's hit and miss, but yeah, a lot of them can. Certainly some of them are based on using those different techniques that I gave you. Phosphorescence imaging is a very popular technique. And when you're imaging something, you can obviously image the entire stone, and they write computer programs that will actually pinpoint which stones in a ring or in a piece of jewelry are phosphorescing, so you know those are the problem stones. Other technologies like ours focus on a stone-by-stone basis, which takes longer, but it also gives you information that you can't get from a lot of stones all at the same time. So it's a mixture of both is the answer to the question. But yes, you certainly can do that.
Okay. All right. We have a couple questions about HPHT-GROWN pink diamonds. Can you perhaps summarize a little bit about what sort of fluorescence and or phosphorescence you might see in pink HPHT-GROWNs?
So if I go back a slide here, these HPHT-GROWN diamonds are pink, and to give you probably more information than you want, the pink color from stones that have been treated like this to pink from post-growth is from a defect called the nitrogen vacancy defect. So when you irradiate the diamonds, you introduce vacancies, meaning you knock carbon atoms out of the lattice. So to get a nitrogen vacancy defect, you obviously have to have a nitrogen and a vacancy. So radiation makes the vacancies. You have to already have the nitrogen from the HPHT growth. To get those two to become a couple, you then have to heat the stones and make those vacancies move around so that they run into the nitrogens and you have nitrogen vacancy defects. One of the byproducts of nitrogen vacancy defects is that they fluoresce very strongly, and they tend to fluoresce sort of an orange to a red color, depending on the other defects that are present. So in a nutshell, the answer to that is HPHT lab-grown diamonds are probably pink diamonds that have been treated pink are probably going to fluoresce or not phosphoresce, just fluoresce an orange to a red color. It may be weak, but it's something that you don't see very often amongst the other stones. So
we do have a couple other questions. One is, how many meli can be grown in a HPHT single press at the same time?
I don't know the answer to that directly. It's a lot. They can grow several carats worth of meli all at once in an hour in each of those presses that I showed you, the lines and lines of presses. I mean, if you think about each of these meli is about a couple of points, and they're growing, at least 3 years ago, they were growing 200,000 carats of this stuff per month. It gives you an idea of just how quickly they can grow it. But yeah, you can grow several carats of meli every hour in each press. So it's a lot.
Just going back to the screening instruments, what sort of questions should people ask when thinking of purchasing one of these instruments?
Well, I mean, obviously it depends on what your needs are. One of the questions earlier mentioned loose stones versus mounted, and being able to look at a lot of stones all at the same time. I mean, if I'm in a business where I'm evaluating 100 meli in each ring and I'm looking at 100 rings a day, I want something that can screen stones very quickly, and I can do whole rings at a time, that sort of thing. Versus if I'm doing loose stones, then I may want to be able to see each individually and keep them separate, that sort of thing. You want to know that, and then I highly recommend that Project Assure results site, because they did several bits of testing. They did normal, decent sized stones, then they did smaller stones. They tell you whether it can detect simulants, whether it can detect just lab grown stones, whether it can detect. So it really depends on what your needs are, but those are the types of questions to ask. Can I also detect simulants? Can it do mounted? Can it do loose? Can I determine, is it 100% accurate? I mean, is it going to call 1 out of every 1,000 lab grown diamonds natural? Because that's a problem in our business. So just how accurate it is. But I mean, those are the basic questions, but I highly recommend checking out the results on that site, because you'll get a lot of what you're asking for, I think.
One person had a question about how long should we expose a diamond to shortwave before we turn that shortwave light off to see the phosphorescence?
For these lab grown diamonds, it really doesn't take long at all. The handheld shortwave lamps out there, most of them are done with a mercury lamp, and it's a lot of output of shortwave UV. So just hold it right down onto the diamonds, and pretty much after, I don't know, 10, 15 seconds, you can turn it off, and you should see them phosphoresce if they're lab grown, HPHT lab grown.
Okay. Are there any other inclusions that one might see in a stone that could, I mean, other than iron or metal, that would indicate that it's lab grown or simulant?
I mean, if we're talking about larger diamonds, those are by far the best. I mean, simulant is a different question. Well, you address lab grown first. HPHT lab grown diamonds pretty much just show metallic flux inclusions, or occasionally these little sort of breadcrumby cloud particle inclusions that are very distinctive. But you're not going to see any of that in meli. I mean, you might see some flux inclusions if you have a really high magnification, or if it's a larger meli stone. As far as CVD, lab-grown stones go, there's really not much to go on. Occasionally, you'll see some wispy black conclusions, but those are not diagnostic of CVD. So you're really stuck on the most distinctive identification feature of a lab-grown diamond inclusion-wise is metallic flux. Now, if we talk about graining, you sometimes see hourglass graining, where the edges of those growth sectors can be seen, where sort of that square and arms, you can see the corners of that. If you can see that in the graining, that's somewhat useful. But once again, that almost always occurs in colored HPHT lab-grown diamonds, and you're not going to see that in very small stones. As far as simulants go, that's a bit of a different story because simulant can be a lot of different materials, and different materials have different inclusions in them. So you kind of got to be wary of that. I don't really want to comment too much there because what I say for one simulant might not be true for another. So.
Well, thank you for that. I have one question about orange diamonds, asking about how rare they are and whether there's any lab-grown versions of orange diamonds.
Oh, it's interesting because you're very lucky to have a webinar on orange diamonds here in about a month that I'll be hosting about yellow and orange diamonds. So if you tune in, then you'll learn a whole lot more. But yes, there are natural orange diamonds. Pure orange diamonds are very, very rare and really, really valuable. Natural diamonds with orange hue components are fairly common amongst yellow diamonds. It's caused by nitrogen primarily. As far as lab-grown diamonds, yes, if you grow a lab-grown HPHT diamond with enough nitrogen and impurities incorporated into it, it can start to become an orange color. It's typically a yellow orange or an orange yellow. You typically don't get pure orange, but certainly will look orange to the eye. So super common, but they're certainly out there.
Okay. I think that may be all the time we have for today.
All right.
I think we'll wrap up the questions. If you have any lingering questions, please find us on Instagram, Facebook, LinkedIn, and Twitter. Thank you all for coming and joining us. Again, next week, we will be joined by Dr. Karin Smit, who will be discussing the formation of natural yellow type 1B diamonds. And thank you once again to Dr. Mike Breeding for your excellent presentation. Thank you.
Thank you, everyone.